Okay, so I'm going to do a wrap-up recording on this section, which is following the while loops, but our main things that I'm going to be looking at here are the bitwise operators. So I'm going to be dealing with figuring out the least significant bit, the bottom 4 bits, the words to bytes, and the printing out the binary bits are the 4 that I'm going to do in this particular section, or as many of them as I can get done before I have to leave it. So we'll start out with the least significant bit, and for that program you're asked to take in an integer and determine if the bottom bit is a 1 or a 0. You could test this by just checking if it's odd or even. If it's an even number, it's least significant bit is a 0, and if it's odd, its least significant bit is a 1. But we're going to do it by the bitwise operators. So take in an integer input, and what we're going to do is we're going to test if input, and we're going to AND it, single AND, with 0x 01. Now you're effectively just ANDing with 1, but we can do it, we may as well put in the whole lot of it here for the moment. Now, if the result of this is, so just putting in the extra bracket is tend to confuse me, so just if that is a true value, the if statement will be true, and therefore it means that we have a 1 in that position. If it's not, it'll be false. Now, but if you'd like to make it explicit, you can say is equal to. Well, we say not equal to is the better way to do this. Not equal to 0. The reason I say not, it doesn't matter in the case of the least significant bit, but all the other ones it would matter, because it would either be 0 or non-zero. It wouldn't necessarily be a 1. Least significant bit is a 1. Okay. And obviously we have to ask for the input, so printf. Oh, put the bracket in the wrong place here. Okay, so 5, which has the least significant bit of 1, and we'll try a 4, which has the least significant bit of 0, so that bit's working anyway. Okay, so that's the first program, which is the least significant bit. Now the next thing we have to do is we have to get the bottom 4 bits. Okay, and it's the number represented by the bottom 4 bits. We don't actually print out the 1s and 0s of it. So in the previous case, if we had something like a 5 that was 0101, and we were ANDing it with 0001, and as you can see in this case, a 1 ANDed with a 1 will give us a 1. Any of the others, like this one, 0 ANDed with a 1, will give us a 0. So we would have got a 1 as a result out of that. If it was a 4, which is that, we would have got a a 1 and with a 0, which is a 0, and all the others would have been a 0 as well because one of the elements was 0. So in the next case, what we have to do is we have to deal with numbers that are bigger than that. And we have to figure out what the number is that's represented by the bottom 4 bits, and that means setting these 3 here all to 1 so that we find out what the bottom 4 bits are equivalent to. So we take our input here, so I'm just going to take out this section here out of this program. We take in an input and we're going to find out, just make another integer, int bottom 4 bits, and what we do is we say bottom 4 bits is assigned input, and we AND it with 0, x, 0, f, because f is all ones in the bottom section. Okay. Now if I take a number, and I'll just see if I can find my calculator here. I'm not fully used to this computer yet, so I'm not sure where the calculator is on it. Thought it might be in some of this bunch, but it clearly isn't. I see it. Now hopefully this will have the right type of calculator for me. Now unfortunately that's not giving me a scientific version, so that won't do me at all. In any case, what I'll do is I'll just do it on another machine. Hopefully you'll have a calculator on your machine, or you can use your ordinary calculator. Just going to take a number such as 569 in decimal. And in binary, that is the following. I'll just write it out for you. 10001110001. Okay, now the bottom 4 bits of that are these 4 here. 1001 is a 9 in decimal. So that's what we expect to see printed out at the end for this one. Okay. Okay, so just remember that example, the number I put in was 569. And the bottom 4 bits represent a 9, so we know that this program is working now. Okay. Now my next program is to words to bytes. Okay. So what we want to do here is we want to take some number, and the numbers could be up to 32 bits in length, and we want to be able to split that into 4 individual bytes, and those individual bytes have to be independent of each other. So we don't just print them, we need to actually make the numbers. So I'm just pulling up the program here. So it has to be put into its 4 different bytes. Okay. So I'm going to leave the input there as that. And you'll remember there was a video there to do with shifting. Okay, so that should hopefully assist you with what we're going to do with this next program. So I'm making 4 individual bytes that I'm going to put these into. And we'll assume that byte 1 is the high byte and byte 4 is the low byte, but you can make that decision yourself. So byte 1 would be equal to the following. It would be equal to input. Input has to be ANDed with 0x ff, which is the top byte, but then another 3 bytes below that. So that's what it's going to be ANDed with. That will give you the number, but unfortunately it'll be in the incorrect position. Okay, so just to show you here, if I was to give you an example. Okay, so there's your 32 bits, and we're ANDing it effectively with the following. All zeros there, all zeros there, and all zeros there. Now that's going to give me the following as a result. Okay. Which is not exactly what I want, because I want to isolate just this byte. So to do that, what I have to do is I have to shift it in this direction, and I have to shift it by the number of bits that are here, which is 8 and 8 and 8 together is 24. So I have to shift it 24 spots so that what I end up with is just that at the end. Okay, so I'll just comment this out here for the moment in case I need to use it again. That pattern there of 10101010, that's given by the hex AA. So I'll know that when I'm putting it in. So what I need to do is to take this and then to shift it 24 spots. Okay. What I then do with the next one is byte number 2 is I'm going to do similar, which is why I'm copying it, but this time I'm going to put the FF here. Now it doesn't really matter, I'll do it just to make it a bit more explanatory here. It doesn't matter if I put the 00 there or not at the beginning. And this time I shift it 16 places because we're dealing with this byte here. It's this one that's all ones now, and this one that's zeros. Okay, and therefore my result is going to end up down in this section here, and I need to shift it the 16 bits that are from there to there to move it down. So for byte number 3, you've probably figured it out at this stage. It's I'm going to move the FF to there, and this time we're going to shift it 8 bits. And finally byte number 4, we don't bother shifting this at all because it's down in the correct position already. So it's FF there, 00 there. Okay. So we're just going to print these out. Okay. The other thing I'm going to do is rather than use %d, I'm going to use %x to take it in as a hex value. I always find that that easier when dealing with things that are going to be readily changed into binary numbers. So what I will do is I'm going to output this pattern here. That's AA. You can check these on your own binary calculator, binary text decimal. That's AA, that's FF, that's 88, and this is 55. So AA, FF, 88, and 55. Oh, sorry, I hit it too fast there. Let me do it again. AA, FF, 88, 55. And we can see that it's printed out the bytes 170, 255, 136 and 85. So what we'll do to make it a bit easier on ourselves to make sure that it's definitely separated those properly is we'll also put these as %x. And once again, and we can see we have the AA, FF, 88 and 55 are printed out. So that's how you split them into 4 separate bytes. And each of those bytes are separate. They're not just printed, they are actually stored in those individual integers. Okay. Now I think the final program that we have to look at is to print out the binary bits. Okay, so write a function that is passed an integer from the user and prints out the binary bits associated with the integer. The function doesn't need to return anything, it just needs to print things out, and then write the main function to test your function. So, I may as well start a new program rather than overwrite that one, because this one's significantly different. So we'll take a number. Now again, what I'm going to do with this is I'm going to take it in as a hex digits, because it's easier for me to look at. So %x. So I'll say that please enter a number as hex, just so that the user knows. %num, and then we'll call the binary bits function, and we'll send it num, which of course means I have to write the binary bits function. So that's the next thing. Just save the file as it is. Never leave it till the end to save, because otherwise you could lose a lot of your work. Now, we said the binary bits function does not need to return anything, but it does need to be sent an integer. Now, what I'm going to do is I'm going to create an integer here called a mask. Now, sometimes, and I think this may be one of the situations, I may need to put that as an unsigned int mask, but I'll leave it as it is for the moment. I'm going to set that to the following value, which is going to be 0x8 0 0 0 0 0 0 0. Now, just to show you, down here, I'll write it as a comment. This represents the following number 1. Okay, so that's a 32-bit number with the top bit being a 1. And so what we're going to do is we're going to AND that with the top bit of num and find out what the value is. If it's a non-zero number, that means that the bit in num was a 1. If it's a 0, it means that that bit was a 0. So we can do a for loop here, and I sign 0, I smaller than 32, I plus plus. And we're going to run this 32 times, so that means I need to write an integer called I there in order to do that. And I'm going to say if num and mask num attribute mask is not equal to 0. So not equal to 0. Remember that it won't necessarily be a 1. It'll just be not equal to 0. Then I print out a 1. Else I print out a 0. Okay. Finally, in the if statement, because this will only work the first time if I add it with the mask, but what I need to do is I need to say the mask is equal to the mask shifted by 1 spot, because we're going to move it 1 spot each time. So what's going to happen is the next time around, I'll just copy the whole lot of this so that and hopefully I remember to put a semicolon up behind that 1 when I go back up, otherwise I'm going to get an error. So next time around, that's going to be a 0, that's going to be a 1, and we're to there, okay? And then we're going to move position, we're going to move it to there. Okay, and you can see that the 1 is moving diagonally over the way until it goes 32 times, until it moves all the way over. So it's going to test each bit along the way. Okay. Now, the danger is, though, that when we shift, whether we take a 0 in from outside or a 1 in from outside, and this could be, if this is not a signed, if this is a signed number where the top bit actually represents a minus number, it may continue to have minus numbers all the way and keeps bringing in 1s, so that may cause an issue. Now, what I'm going to do is I'm going to just test that. So I have a feeling this won't work on the first occasion until I change that to unsigned. I'm going to put in my example, which was AA, FF, 88 and 55, because I know what they look like, and you can see I've got a string of 1s, so that's clearly wrong, and this is caused by the mask here being signed. So just to make it clear that that top bit there in a signed number represents a minus. Okay, so this is a minus number, and therefore it's going to continue to be a minus number after we shift it. Now we'll try it again now that it's unsigned, and it's AAFF 8855, and this is looking much better. So we can see all of my bits there, 10, 10, 10, 10, all the 1s for 8. Then we've 0, then we've 1 0 0 0, 1 0 0 0, and then 0 1 0 1 0 1 and 0 1s. That has worked perfectly. Okay, so that's the printing out of the binary bits, and that's how it's done, split up into the 2 different sections.